Hello everyone, and thank you for joining us for today's webinar. My name is Neil Foley and I'm the Applications Engineer here at RIZE, and today I'm going to be talking about FEA simulation visualization with full color 3D printing. So first, quick introduction to some of the things I'll be talking about. First, I'll go over some general ideas of FEA simulation, what it is and what it's used for especially. Then I'll talk a bit about full color 3D printing in general, and once again what that's about and what it's useful for. And then we'll look at combining the two and some of the benefits you can get from that, including enhancing your ability to visualize simulations, as well as enhancing your ability to communicate about the results. And then finally, I'll talk a bit about best practices throughout this process and do a quick software demonstration of implementing this combination of technologies. So first, here is a general overview of finite element analysis, or FEA as it's often called. This is a method of modeling physical systems as collections of small connected elements. So typically this will involve taking a CAD model and through the software breaking it up into small connected pieces, and then depending on the type of simulation you wish to run on it, those pieces will be constrained and influenced by a variety of effects, and then they will simulate those effects over time and produce some map of data throughout the points or across the surface that will tell you the types of things that will be affecting each point on the object. So implementing finite element analysis essentially involves defining the geometric constraints that are going to be affecting the object, and then, or that are going to be constraining the object, and then applying various external effects. So this could include forces or temperature applied through heat, as well as fluid inputs and outputs. And using these different types of effects, you can model stresses, temperatures, and pressures or flow rates of fluids as mapped over the surface or the internal volume of a part. All right, so here is a quick overview of RIZE's unique 3D printing process and how we're able to use this technology to perform full color 3D printing. So RIZE combines two basic technologies that are used in printing. One is material extrusion, in which thermoplastic material is extruded through a heated nozzle, and layers of an object are essentially drawn in plastic onto a build plate layer by layer. The second technology is material jetting, or ink jetting, which is using the same type of technology that you would find in many 2D printers, wherein fluid inks are jetted out of a printhead as it passes over a part. So combining these technologies typically involves beginning by extruding support material onto the build plate, and this can be used as support for the underside of the part. Then a special ink that we call a release ink is jetted between the support and the model structure, and then the model continues to be extruded layer by layer, while additional functional inks, including colored inks, can be applied onto the internals or surface of the part as it builds. So this is able to achieve all sorts of useful effects, including full color 3D printing through the implementation of different colored inks. So here are some of the many effects that can be achieved using this technology. You can see that there's product design, prototyping, there is GIS, map production, which is useful for geography, geology, and in some cases architecture. It's useful for visualizing biological systems in the life sciences and having physical parts to use for that. It's also useful for what we're talking about here, FEA simulation visualization, and the technology in general can be useful for a variety of other parts that are not necessarily produced with full color. So here are some example parts of the types of models that you can run simulations on and generate full color 3D printed parts from. So we have a variety of different examples here. On the bottom left is a connecting rod, which shows the stresses that are developed in this part as it operates within an engine. In the top left, there are several different types of cross sections of I-beams and other types of beams that are used for construction. And not only do these show the color map, they also show the deformed shape of the object after the forces have been applied. This is exaggerated, of course, but it shows the directions in which each point on a part might be deformed in. Then in the bottom right, we have a generatively designed part which used topology optimization to create an optimized surface shape for a variety of constraints that were initially applied to the model. And then this also has stress mapping over all of the places where you would find the typical forces applied to this part would develop large stresses in it. So now I'll talk a bit about the ability for combining these technologies to enhance visualization. So one of the benefits of using 3D printed parts that have color mapped over their surface rather than just using it in a CAD software that performs the simulation is that it's more natural to view and manipulate an object with your hands, just because it's so much more common for people to do this sort of viewing and manipulation. So having that closer connection to the physical part allows you to, in some ways, more naturally analyze it and find where any issues may be present. It also allows you to do tactile examination, which is the same sort of thing. You have a more natural feel for it, and you would be able to identify issues perhaps more easily than by rotating a 2D projection of a 3D part on your screen. And finally, one of the useful things about having an actual 3D printed part as a result of doing FEA simulation is that you can then use that part to do an actual test of the stresses that you expect to be incurred on the part and see if the simulation is accurate. Of course, this will be dependent on how effectively the 3D printed part can simulate the internal material properties of the eventual part that you intend to produce. For example, if you simulate a part to have isotropic material properties, then many 3D printers would not be able to effectively simulate that because they are not isotropic. In the case of RIZE's technology, while our parts are not quite isotropic, they are approximately 90% isotropic. So that would be the Z axis is about 90% as strong as the X and Y axes, and this is quite good for 3D printing in the thermoplastic world. So in our case, we would be able to use this technology quite effectively to test whether the results of the simulation are mapped accurately onto the eventual part. So in addition to being able to visualize parts more effectively, which can be helpful even to engineers who are used to working with 2D projections on their screens, it can also be useful to provide 3D printed versions of simulated FEA data to people who are less used to working with 2D projections on a screen like that, who maybe don't have experience with CAD software or don't have access to it. Being able to hand them a 3D printed part is very often a much more natural way to introduce them to the sort of effects of the data that you've developed through your simulations. So This is a method that allows you to provide parts across distances. Printing parts allows them to be transportable, presentable at meetings, shareable around the room. These things can be passed from person to person without worrying about them breaking, of course, and it's a much more personal effect that it can have on each person than everyone looking up at a screen and trying to understand it as someone else rotates the part. So this can allow these advantages that I've discussed to be shared to boardrooms, client visits, and exhibitions, where having a part in hand makes the effect of these simulations much more personal to the people who are examining it. So overall, because of this, it allows you to reach a wider audience with the comprehensive simulation results and enables that audience to make more informed and better development decision making. So next I'm going to switch over to SolidWorks to do a quick demonstration of some of the things you'll want to pay attention to while doing simulation analyses. So this type of technology is present in a variety of different CAD tools, not just SolidWorks. SolidWorks is the one that I'll be using to demonstrate it today, but it's available in several other forms as well. So I'll be going over quickly how to set up the simulation in SolidWorks and some of the things to look for. This will include, in our case, opening existing STLs. So this would be useful for people who want to demonstrate the material properties or other FEA simulation effects of a part after it has already been exported to an STL, or perhaps if they only have the STL available to them. I'll also discuss how to define constraints accurately and make sure you don't make some simple common errors. And then we'll look at min and max values of color mapping, which can help you get just the right effect of the range of color on the parts that you eventually print out. And this will give them the best visual effect on those who hold them. And then we'll also look a little bit at what effect using the deformed and undeformed geometry can have on the, once again, visual effect of the part. And then finally, I'll talk quickly about how to actually get this part ready for 3D printing using exporting and importing VRMLs. Right, so here we have SolidWorks, and this is that I-beam part that we saw on a few slides. So it's quite a simple part, has one hole here because it's a good part actually to print out and put on a keychain. So there's a hole there just to hook it onto something for demonstrations. So over here, we have this simulation tab, which gives the options for starting a simulation. All we need is new study. If you haven't used simulation before, I believe it is standard, or it is present in the standard version of SolidWorks. All you need to know is that the way you get it loaded up is you have to go to Tools, Add-ins, and then make sure it's selected here. And if you want it to open on startup, you can check that off too. So all we have to do to start a new study is hit this new study. The standard default options will be fine for us now, so we'll hit OK. And that gets our study started. So now here's our list of the different options we have when controlling before we run the study. The main ones we're going to be paying attention to are fixtures and external loads. So fixtures are going to be the ways in which the part is going to be geometrically constrained. So in this case, I'm going to use just a fixed geometry, and I'm going to apply it to this face back here. So here's one of the things you'll want to pay attention to when constraining your geometry. You'll want to make sure that the type of geometry that you're selecting is the actual portion of it that you want to be constrained. For example, if I wanted to constrain over here and I just clicked this edge, that would not constrain the entire face of the part. And even if I went around and constrained every edge, that would be a very good approximation of what I'm looking for, but it wouldn't quite be precise. So if precision really matters to the data that you produce, then you'll want to pay attention to making sure that you select precisely and only that geometry that you want constrained. So I have constrained that and made it fixed geometry, so I can click OK there. And then let's see. On the other side, let's do an elastic support. And I'm going to actually put that on the bottom face, if it allows me to. Yep. And I'll just throw a number in here. So the numbers that you use are, of course, going to have a large effect on the results of the simulation. However, oftentimes if all you care about is the visual effect, then the absolute numbers aren't all that important. What will really matter is the relative effect of each number. So the ratio among the numbers that you use is going to be more important. So I haven't really calculated what would be reasonable values to use here for a size of this part and material properties, but just using sort of stand-ins will work fine for us. So next you have a variety of different types of loads that you can use. So I'm going to start with gravity and let that be applied right there in the center. And then I'm going to apply some pressure, and I'm going to apply that pressure, let's put it right here, see what that does. All right, so we've got some constrained geometry with the fixed face over here and the elastic support across the bottom face. And then we have a few different forces affecting the part. We have gravity and we have pressure over here. The next step would be to mesh the part. This is the step where the overall solid geometry of the part is broken down into small pieces, which can be simulated independently and not exactly independently, but they can be simulated as singular components and relate to one another rather than trying to model a complex part in an exact analytical way. So the next step would be to mesh the part, and this would break it down into those small pieces, and then you would want to actually run the simulation. You can just use mesh and run, and it does it in one step, and that will produce the results for you. One of the things you'll want to pay attention to with mesh is that if you have a very large or complex part, having it be large isn't all that important unless you're breaking it into small pieces relative to its overall size. In some cases, such as the generatively designed part that was shown on a few slides previously, if you have a complex part like that, then it may be helpful to reduce the resolution of the mesh. I know that my computer struggled to run the simulation and failed several times because the process just couldn't handle the amount of complexity on a part that large, complex broken into so many pieces. So there are a variety of different options. You can use constant or variable resolutions, and all of that is stuff that you'll have to look into on your own. It's a little bit outside the scope of this. So the simulation typically takes a minute or two to run, maybe more if it's complex, so I won't bore you with that here, but we'll just look at a few of the other ones we have. So this is a simple simulation of a version of this that you've already seen. Once again, it has one fixed face over here and one face over here that has torque applied to it, and we already have the results produced by the simulation, so we can just look at some of these. So I'm going to show displacement. That illustrates a gradient over the part, depending on how much each point of the part was displaced. So in this case, you can see exactly that the red portion has not moved and the bluest portion has moved the most. I think I actually swapped these colors so that it would be red on the bottom and blue on these corners. But one of the things you can do is hit this deformed result button, and that will toggle back and forth between showing the original geometry of the part with the colors mapped to it versus showing the geometry of the part deformed in the way that it would be deformed if these forces were actually applied. Now, I believe this simulation was run on, what is it, alloy steel here. So this is not the actual effect that this torque would have on the part. It wouldn't be nearly that pronounced, but using a deformed result sort of exaggerates it just to get a visual effect that can be recognized by the naked eye. So if you are interested in printing a part that has this effect, which can show not only the colors to those who are looking at the part, but the actual motion of each of the components of the part after forces have been applied to it, then this is something that maybe could be useful to you. So I have a few others that show some different things. In this case, we had two fixed faces and pressure on the top. And this has somewhat of a cool effect. So some of the things that you can do with this include changing the color settings, and sometimes I'm actually going to switch to another chart. So a lot of times you'll find that while displacement will be mapped with a large variety of colors, if you're interested in showing stress, you probably won't see as much because stresses tend to be very high in a very small area and of course lower over a larger area. So it's less common to see a large amount of stress over a large amount of area because stresses are of course highest where they're concentrated. So in this part we have a few points of red and the rest of it is really just blue and green. So if we are interested in showing people a bit more resolution in the variety of different stresses over this part, one of the things we could do is change the range of colors that are being shown using these chart options in the settings. So by default, it automatically defines the maximum and minimum values. What we can do here is just change these numbers to get this range. The part is in this a little bit that if we were to reduce this point down to, let's say, 1.8, then a lot more of this part would become colorful and more visually interesting and illustrative. So that's probably a bit too much, so we might want to raise it back up to, let's say, 20. And just focusing, yeah, that looks all right. So this shows larger stresses in a couple different places, and we have a good range of colors. So this would be a pretty good part to illustrate the effects that are happening on this part. In some cases, you may not want that. You may want to restrict it to just the very highest stresses, because what you really care about in a lot of cases, of course, is just going to be the failure points, the small areas where the stresses are really highest. So anyway, I think that covers most of what I wanted to. Now I just want to talk a bit about the types of files you'll be working with. So I'm going to close out of this. One of the things that you may want to do is, rather than working with a SolidWorks part, is perhaps work with a part that has already been exported into an STL, and perhaps you don't have the original version of it. So if you are going to be working with STLs, one of the things you'll have to make sure you do is from this options menu where you're going to open the part, make sure that you go to options here and make sure that this is selected to solid body. I believe the default is graphics body, and if you have graphics or surface, then it's not going to allow you to run a solid simulation. So you have to stick with solid bodies for this. And then if I click OK, it'll load it up. Yeah, I'll open this part up quickly. All right, it's gonna go. So the easiest way to tell whether or not you'll be able to run a simulation on a part is to check whether the part is actually solid, and the easiest way to check that is just to go to your features tab and see whether it's possible to remove material from the part. So if this ever loads, then yep, there we go. So if I go to the features here, you can see that I have this whole panel here that allows me to perform cuts on the part. And this means that I have a solid material that's capable of cutting through. If this had been imported as a surface or graphics body, then these options would be available and these would not. So I don't know how this will look exactly in other types of software, but I expect that they would have similar sorts of effects where you would be restricted from using these if you don't have the right type of file in use. So I'm actually going to switch back now up here. Oh, I think I opened a file that's too big for it. All right, so the one other thing that you'll want to do in terms of using files with SolidWorks is from your simulation, the best way to get the color that you've developed on the part is to just right click on whichever one of these simulation runs that you want to produce as a 3D printed part and go to Save As, and then you can select WRL, your ML files, and save it like that. And from there, I can go to our RIZE software and open it right up here. And there we have our part. We can move it around and slice it, prepare the job as usual. All right, so that's all I have for using full color 3D printing to visualize FEA simulation data. Thank you all for joining us for today's webinar. I'm going to be sticking around for a few minutes in case anyone has questions. If you do, you can type those questions into the chat window at the bottom of your GoToMeeting panel, and I will answer those as they come. If you aren't sticking around for questions, remember that you can always reach me at applications@rize3d.com. And other than that, please have a nice day.